Hello everyone, my name is Zeping Yu. Today I'm going to introduce our work in EMNLP 2024. The title is How do Large Language Models Learn in Context? Query and key metrics of in-context heads are two towers for metric learning. In-context learning is an emergent ability of LLMs. It can perform an async example based on input label pairs. The right figure shows an example of sentiment classification. Given several sentence label pairs, the model can predict the correct label of the input sentence, a smile on your face. It is very surprising because this is done during the inference time without gradient design. If we understand the mechanism of in-context learning, we can design methods to improve the accuracy of many downstream tasks and also the train of thought ability. Many studies have explored in-context learning. Private studies find that the sentiment-unrelated ICL is the emergent ability of LLMs. For example, we can use the sentiment-unrelated labels, full and bar, to replace the ground truth labels, negative and positive. LLMs can still predict the correct labels, but small models can't. This is because larger language models can learn the input label mappings, while the small models can only learn the semantic para. Another study analyzed this phenomenon and found that there are two tasks in context learning, which are task recognition and task learning. Task recognition means the ability to recognize the task, and task learning means the ability to capture new input label mappings. Regular ICL cases require both task recognition and task learning, but only task learning is an emergent ability of LLMs. And another study explores the ICL mechanism by analyzing the information flow. They find that the label positions are the anchors to extract information in shallow layers and be used in deep layers. But we hope to understand more about how this happens. For instance, which heads are important, and which are the roles of the query, key, value, and output metrics in the attention heads. There is already a mechanistic interpretability work studying the copying mechanism by induction heads. Specifically, they do experiments on an attention-only two-layer language model and find that two attention layers can have the copying ability. Take the sentence in the figure as an example. In the first attention layer, the TERS position extracts the feature of its previous token POT. In the second attention layer, the later POT position has large attention score, with the captured POT features on the TERS position. So the TERS is copied into the last position and be predicted as the next token. Based on the previous studies, we propose the hypothesis of in-context learning mechanism. In shallow layers, the label positions extract the demonstration features, and the last position extracts features in all positions. In deep layers heads, the query and key metrics are two towers learning the similarity metric between the last position and the features on the label positions. The value and output metrics extract the label features on the label positions. The similarity between the input text and the demonstrations play very large roles. Here is the mechanistic interpretability evidence we found in GPT-2. The example is love bar, like bar, 8 full, 2 full, 1 watt. The prediction should be full because full is the semantic unrelated label meaning number, and bar means sentiment. We first identify the important heads and project the vectors in embedding space. We find that the value output vectors are related to the labels, and the query and key vectors are related to the demonstrations. This evidence can support our hypothesis. Then we design experiments to verify the hypothesis. We do experiments on 5 sentence classification datasets, and we random sample 2 demonstrations with each label. The labels of S0 and S1 are the same, and the labels of S2, S3, and S4 are the same. We run the experiments in Llama and GPT-J, and the ICL accuracy is high on most datasets. Then we identify the important heads using causal-based and logic-based methods. We find 6 full heads which are very important for predicting full, and 6 bar heads which are very important for bar. Specifically, when using 0 vectors to replace the parameters of these heads, the ICL accuracy decreases very much. So we name these heads in-context heads. Then we want to find which positions are important in these in-context heads. We design a logic minus score to evaluate the information storage. The minus score is the minus of the log probability of full and log probability of bar by multiplying the embedding matrix. If the logic minus is large, it means the vector contains more information about full. If it is smaller than 0, it means the vector contains more information about bar. Each attention head output vector can be regarded as the weighted sum of the value output vectors in every position, where the weight is the attention score and the value output vectors are the transformation of each position's layer input vector. We find that the full positions in full heads contain much information about full, and the bar positions in bar heads contain much information about bar. So the in-context heads mechanism is a copying mechanism. When we reverse the labels of each demonstration, the prediction will change from full to bar. We hope to analyze what causes this change. We compute the change of the logic minus of the weighted value output vectors, the attention scores, and the logic minus of the value output vectors. We find that the attention scores change very much. So the changing of attention scores on full and bar positions causes the probability change from full to bar. Based on this evidence, we propose the hypothesis of in-context learning. Take the sentence in the figure as an example. The sentence is France bar, cat full, dog what? The prediction is full, because full means animal and bar means country. In shallow layers, the label positions extract the demonstration features, and the last position extracts X% dog, Y% cat, and Z% France. In deep layers in-context heads, the value output matrix extracts the label features full and bar. The similarity between the last position's features and the second label position's feature is larger because this position has the features about cat, and cat is more similar with dog. As a result, full is the final prediction. And we utilize this hypothesis to understand and reduce the majority label bias in in-context learning. The majority label bias means LLM tends to predict the label with more demonstration label pairs. We find that this reason is the label's attention score decreases when the demonstration label pair is removed. So we propose a method to reduce the majority label bias by enlarging the attention score of the imbalanced label in in-context heads, and the bias is reduced much. We also utilize the hypothesis to understand and reduce the recency bias in in-context learning. When the order of the demonstration label pairs change, the ICL ability is affected much. We find that this is because the computation of the attendance score has a constant term about the positions. So we remove the positional term in in-context heads, and the recency bias is reduced. Here are the contributions of our work. We propose a hypothesis of in-context learning and design experiments to understand the roles of different modules. We understand and reduce the majority label bias and recency bias of in-context learning. Thank you for listening.